Very welcome to the second session. So in this session, we are going to talk a bit more technical about logical structure of dynamics that we are going to dealing with in the whole course. So all of these the mathematical structure that we are referring to is differential equation. But before going there, I'm just taking a quick overview over algebraic equation, which has a kind of form like p is equal to 0. And in general, you can divide it in two parts like univariate and multivariate. If if it just has one variable like x, then it's univariate, and if it is more than one dimension, then it's going to be multivariate, or mostly pronounced or called by polynomial. But the important thing here is that the solutions in algebraic equations are numbers. So let's, for instance, take x3 minus 1 is equal to 0, and then you have a solution for this. Or if you have a set of equations like x5 plus xy plus sine of x equal to 0, and another equation you can solve for two variate for polynomial forms of algebraic equation, which I am sure you are quite familiar with. So the order in our algebraic equation is the highest order of the variable. Like, it's very simple. Like, if we have x3 plus x2 plus 1 equal to 0, then it's going to be 3. These are just getting familiar a bit to the terminology. So the linear function has two conditions. This linearity is very important because we are going to talk about a new way of solving and getting a qualified picture about nonlinear functions. So it's important to have this idea that what does linearity mean actually. One of them is additivity, the feature, and the other one is homogeneity. So additivity, you can say, for instance, take a function like f of z equal to z to the power 2. Then if you have something like f of you can take a number, or maybe it's better to write it in variables. So it's going to be like x plus y to the power 2, and this is x2 plus y2 plus 2xy, which clearly it is not equal to x2 plus y2, because of this. Therefore, this is a nonlinear function because it's not first power, and this additivity doesn't work here. Or if you have a function like, for instance, take fz is equal to 3z, for instance, then both of these conditions are satisfied and stay valid. Therefore, it is linear function. So let's go to differential equation. The difference between differential equation and algebraic equation is that you are going to deal with changing, with finding the behavior of your function by changing variables. Mostly we talk about time, but the solution in this equation will be functions in spite of algebraic equations. So it again has the order, and the first order here will be like I am going to show the derivative in respect to time, like v dot, and by this v dot or v prime or d over dt, or this v by the index of t, all of them are same. They are just the representation of the first derivative in respect to time, to t, you can say, whatever the variable is. And for instance, in this in this example, you can say we have dv over dt equal to 2. Therefore, it's very simple in this sense. 2 times dt, and then you go and take an antiderivative of both sides. Therefore, it's going to be v is equal to 2t plus another constant that you can find by conditions or boundary conditions and stuff. So the second order differential equation, one of the simplest examples is simple harmonic oscillator, like taking take a solid thing like m with the weight of that the mass is m, and the constant of its I forgot actually the name, probably you all know. It's this is a constant, m also is a constant, and this formula here is coming from Newton formula, F equal to ma, and this is a change in the position, which actually refers the second derivative of x. So you want to see how to deal with it, but this is a second order differential equation. Therefore, just to see what should we do for this, we are coming back to this part. Actually, we are so much interested in some forms like x dot equal to f of x. In general, we just try to look and find this first derivative. Therefore, for this part, we have a trick. We are going to say, okay, we have something like x as position, we have something like x dot as the velocity, and x double dot as the acceleration here. But we are interested to find this form, although there's a very direct relationship here between velocity and x, but as a mathematical trick, we are going to say we define another variable, two sets of variables, like x1 is equal to x, and x2 is equal to x dot, like the velocity and the position. And therefore, from this relationship, you will see that actually x2 is equal to x1 dot, and also from this equation you can find that actually so you can write it like this, right? X dot 2 is equal to x2 dot is equal to x double dot. Therefore, this is going to be mx dot 2 is equal to minus kx1. And by this trick, you will find that actually you can again replace these things, and we will refer to this. But these are just the trick, mathematical trick to find the first derivative of it. So we just quickly overview on some graphs. So we want to draw something like sine of x, and for this we know that sine of 0 is equal to 0. Sine of p is also equal to 0. Sine of 2p is also equal to 0, and the period of it is equal to 2p. And also we know that sine of p over 2 is equal to 1, and therefore we just it's just important to know some basic things which I am quite sure that you all know and familiar with this. That this is a kind of periodic thing here. It's going to be repeated and repeated. And same for cosine, but it starts from 0, and cosine of x will start from 1. And again it has another period like 2p. About exponential, so e is the natural number, and the exponential of x, you can say e to the power 0 is equal to 1, e to the power minus infinity almost. I mean, you can say that x and the limit of it when x is going through minus infinity, then it's going to be like 0. And you can again take this limit of when x approaches to positive infinity, and it's going to be infinity. And if you just want to draw it, you will write you should find this part, right? So if x is equal to 1, therefore it's here, and if x is equal to if it approaches to minus infinity, it's going to be close to 0, and therefore you have a kind of shape like this. And just keep it in mind that, for instance, if you have a function like y equal to x2, then it's going to be something like this. And so if you have for instance x equal to 2, then for this x2 the y will be 4, but for your exponential it's going to be something, I don't know exactly, but something a bit less than 9. So it's important to know that this what exponential growth actually means. And also you can talk about ln of x, which again you can say that, okay, we does minus, how can we find the value for y which is minus something? It's impossible. Therefore we say that if x is equal to 0, then actually y is equal to so we have actually like this, right? This is log of x with base of e, right? The natural number. So we should actually have a function like this, which is equal to x. So if for instance, let's say that y is equal to 0, what is x? So x is going to be 1, right? So this is the point that it should cross. And if we came from if we just go down through this way, then the y is going to be infinity, minus infinity, I mean. And so you will see something like this. This is also going through infinity, but with you can just have a very slow slope. This is just good to keep in mind what these graphs means. So the order of our differential equation will be the highest derivative in the equation. So here it will be like first order, and here it's going to be again first order, although we had these two, but we are thinking about this just one dot, therefore we call it first. And here we have two dots, therefore we call it second order differential equation. So this was just for getting familiar, and in terminology we have two important classes of differential equations. One of them is ODE, as an abbreviation of ordinary differential equations. So if your function or their derivatives are just functions of only one variable, then you call it ODE. Otherwise, if it is a function of more than one, then you call it PDE. So you can say that, for instance, here I just have whatever the function is. This function is just, I'm going to just talk about this dt, and this brings the idea of one variable for you to take derivative of. So in this ODE, which it's very important for our work actually, and it's the one that we can understand it much more better than PDE, which you have, for instance, two variables or three variables. So just to say that okay, we have a space like consisted of two axes like x and y, which both of them are part of R1, I mean the real numbers, part of R. And so this vector of x, so we call it, like when we show something like this, then it means it's a vector. Or we can also write it something like this. Both of them are vectors. So this belongs to R2. So the dimension of our space is 2 here. Therefore, we, as a general way of this definition, we have a vector of x which is belong to Rn, like n-dimensional thing. And n here actually means the number of variables that we are dealing with. So you can write actually the vector of x like consisted of the variables x1 until xn. And this is very important actually to notice that this Rn here, we call it phase space. We call it phase space or state space. So the desired logical structure of our dynamic will be something like this, that we just have one variable as the derivative, which we just want to look at this simple dot, that the vector of x dot is equal to there's a function like f, which can be also a function of the x vectors, which if we want to write it in components, then it's going to be x dot 1 is equal to f1 as a function of x1 till xn, and x dot n is equal to a function of x1 till xn. So keep it in mind that we have kind of n variables here and n dimensions, but we don't have time. We don't have, for instance, here, for instance, we say that this x dot n is equal to dx dot n over dt, right? So this dt, we don't have this t, and we don't have the function of n doesn't depend on t itself. This is why we call it autonomous system. In autonomous system, we don't have because later we are going to write, as I said, in that phase space like Rn, we are going to make something. Let me write it in another color. Like we are going to write something, to draw something like x dot in respect to x as our phase space, and in this phase space you can find some important things, like if you have a function, if x dot is equal to x2, for instance, then if you just release a ball here, it's just for understanding the concept of it. If you release a ball here, then it's going to be absorbed to this point, right? So this point is an important point. Therefore, you can say that actually there are some things that we will call like vector fields in this space, that any kinds of states of this system. So we call it states. We call any of them as one of the states of the system. All of these states will be going through this absorb or attractor that we will talk about it. But these vectors here or here, they should not change with respect to time. This is our desired thing. This is why we work with autonomous systems, because we want these vector fields to be constant. And if even we have a function which is dependent on t, then we can again define another variable and make it independent. And these functions, like the functions like f1, f2 till fn, they are the functions which is governed, which is given by the system that we are studying. They are the description of the dependencies of these of the changing of the variables with respect to other variables. Like you can say that here for instance we have mx dot is equal to, or a simpler one, v dot is equal to 2. So this is a very simple equation. So let's talk a bit about the linearity. So the linearity is a very important feature actually. The linearity, what does linearity mean? So if we have, we draw those pictures, right? If we have something like y is equal to x, then you will have something like this, right? This is a linear function. And if you say that, okay, this is x dot and this is x, so you have a differential equation, but the relationship between them is linear. Therefore, so you have something like this, right? F of x dot is equal to x. So this x has a feature that brought this kind of linearity. But if you have something like x dot equal to sine of x, then you will see in your phase space, you will see something like this, right? And this is not linear. This is nonlinear, right? We call it linear. We call our system linear if all xi's appear to just first power. So what does it mean? It means that you don't have such a system that you cannot find it, like if you have, for instance, x dot uh, x dot 1 is equal to x2 x3, for instance. You can take it like these indexes are like this, right? X dot is equal to yz, right? So if you have such a systems which are the products of the variables, or you have the powers of them, like x1 dot is equal to, I don't know, like x2 to the power 2, then we saw, right, this is not a linear one. Or if we have a function of xi, whatever it is, like you can take like e to the power x1, which for instance x2 dot is equal to e to the power x1, then it's going to be something like this, right? And this is not linear. So if it is just first power, then we call it linear. So we should take care about checking these three to find whether a system is linear or not. It should be just first power. So now we want to talk about this equation, which was about the simple harmonic oscillator, which we talked about. We wanna figure it out whether it's linear or non-linear and what the order of it is. So we have this equation of mx double dot plus kx equal to 0, and the desired form that we are seeking for is this, right? So for finding this, we can use, as I said before, we can use a mathematical trick and design and define two variables. One of them, sorry, I shouldn't put it in dot. One of them is so x1, we take x1 as x, and also we take x dot as x2. So you can think of it like position and also the velocity. Then we can take another derivative of x dot 1 as well as x dot 2. In this form, we can say that, okay, x1 is equal to x, therefore x dot 1 will be equal to x dot, and x dot 2 will be equal to x from the equation here, x dot 2, which is equal to x double dot, will be like x double dot, then it's going to be minus k over m times x1, right? Minus k over m times x1. Let me write it like this. So we had this, right? We had x dot 1 equal to f1 of here, like some variables, which is x dot that you can write it from this one, x2, right? And also you have x dot 2 equal to f2 of those variables, and it's going to be equal to a constant times x1. So you have a coupled equation here. It means that the change in the variable x1 with respect to time depends on the variable, the second variable, and the change in the second variable with respect to time is depending on the first variable. But you can see that this is first order, therefore this x1 and x2 here, this brings linearity, and you can also figure it out that because we have the second derivative of it, therefore it's second order. But we can write it in the form of linearity, right? How about this part? How about a kind of similar equation, but this one has a term sine of x, which is actually the description of pendulum. So if you do exactly this trick, which we did it before, therefore x1 dot will be x2, and also x2 dot will be sine of x, sine of x1. Therefore here we have a function, right? And we said that if it is a function, therefore it's not linear. So we can write it like non-linear, but still second order differential equation. So about the integrals. In the practice sheet you can find several integrals which are very important, but here we just talk about a few of them. So here you can write the first one like integral of 1, integral of the dx is equal to integral like something like 1 times let me just write like this, right, for not confusing with x. Therefore it's going to be x, right? Or we can write it like the simple, the small x. Also plus a constant like c. So I'm sure that you know all of these things. For the second one, so we have a trick, right? We have a trick like if we wanna use IB trick, it's going to be uv minus integral of v du if we say that this is going to be u and this is going to be dv. So we just change the variables in a form to understand to make it possible to solve. Therefore, so our u will be ln of x. Therefore, du will be 1 over x, and also dv is equal to dx. Therefore, v will be equal to x, right? We have it. So we are going to use it in our formula to solve this integral. So we say ln of x, which is u, times v, which I write it here, minus integral of v, which is x, times du, which is 1 over x. Actually, this is du is 1 over x dx, right? So therefore we have this dx here. Therefore it's going to be x ln of x minus x. So you can also have a constant like c to just find the particular solutions for your integral instead of general solution. For solving this integral, we say we take this part like e to the power of this, like take one, because we need u and v later. So I just, for not getting confused, I take like z as a variable. Therefore, z here is equal to e to the power x2 plus 1, right? So what is z prime? What is z prime? Z prime here you can write it like e to the power of a function of x, right? And if you want to take derivative of this one, you say it's equal to f prime of x times e to f of x, right? Therefore you say, okay, what is the f prime? So you say f prime of x is equal to square root of x2 plus 1 prime, which is equal to, you can say x2 plus 1 to 1 over 2 prime. Therefore it's going to be like, I'm sure that all of you are familiar with this. These are the basic ways of calculus that probably all of you are familiar with. So you say 1 over half, and you also take the derivative of the inside part. So it's going to be equal to, so you omit these parts, and it's going to be x over the square root, because it's going to be like minus 1, right, this part, and it's going to be x2 plus 1, but this is just the f prime, right? So we were seeking for z prime, and for z prime, let me write it over here. I'm writing a bit big. I think I should modify it later. Z prime will be f prime, which is x over the square root of x2 plus 1 times e to the power f of x. What was the f of x? It was this, right? So this is the z prime. So we said this is z, and this is z prime. So you see that here, for instance, this x exists, and we have an x here. Also, we have something here in uh, that we don't have it here, and we need to omit it somehow, which is like yeah, which you can say that this if we have a function, like for instance, take like a variable like p. If p is equal to e to q, then ln of p will be equal to q, right? So you see that we have something here, and we need to create this. Therefore, and we have it in the power of this e. Therefore, we use this as our solution. We say, therefore, what was the integral xz dx, and ln of z will be equal to square root of x2 plus 1, right? This is the ln of z. So the idea is multiplying these two, like these two, multiplying these two. I mean, here maybe you didn't see that. Multiplying these two to find the right form of it. Therefore, we will write it ln of z. So if we write it like this, z prime is equal to dz, right? So we write it like, actually this was just dz, not z prime. So we call it like z ln of z dz will be equal to, so this one part of the solution, it will be equal to square root of x2 plus 1 times x over, from here, x2 plus 1 e to the power x2 plus 1, right? So this part, and this part will omit each other. Therefore, our this is very close to our this is exactly the form that we have in the integral, right? So we actually, and also dx, right? We also have this dx here. When we take this dz, I always forget this part, we also have this dx. So we could actually generate this form. Is a very useful form, and we can write it here like this, x e to the power, we can write it like ln of z dz, right? And for this ln of z dz, we actually solved it here in the second part, ln of x dx, which is same, and you can just write it in this form. Just replace the z instead of x, which z is equal to this. Therefore, you will get the answer. And also, you should also take care about the constants. The constants, you can reduce most of them in just one constant, but after all, you need to find a particular solution for them. based on your condition. That's the particular solution, which you can see and figure it out how to do that, and the solutions are already in practice sheets. And it's very good to recap the integral part, to just make our minds familiar with